Okay, so we have a big section here. We're going to talk about phases and classification of matter. So this is going to include things like states, which you see right here, mass, law, one law we're going to talk about. We're going to talk about elements, atoms, molecules, substance mixtures, a lot. Okay, so this is a big section. So let's get started. So matter is anything that occupies space and has mass. Anything that occupies space and has mass. Let me get my marker ready. Should have had that ready. Okay, here we go. Anything that occupies space and has mass. And there's three of the most common ones: solids, liquids, and gases. All right. Solids are rigid, as you know, and possess a definite shape. So this is a little bit tricky, I think, in the context of, say, a powder. Is a powder a solid or a liquid? Is it rigid? Does it possess a definite shape? And I would say yes, it does. If you look at the little pieces of powder, each of them have a definite shape and they are rigid. Okay, so solids are, or powders are solids, but that's the one thing that always bothers me when I look at that one. Liquids, now, they flow and they take the shape of their containers, but they do have a definite volume. Oh, we should have said that about these guys up here. Watch this. Definite volume, and this also has a definite volume, right? So liquids, you are not compressible. I mean, you can compress them a little bit, but mostly not. And that's why hydraulic jacks and hydraulic lifts can lift so much, because they very much resist a change in volume. So solids have a definite shape and a definite volume. Liquids do not have a definite shape, but they do have a definite volume. And gases have neither a definite shape nor a definite volume. They take both the shape and the volume of their containers. Right, so here's a good example of this. If you take a solid and put it in an Erlenmeyer flask, it's going to be wherever it is, right? Now, a liquid's going to fill out the flask in the shape of the flask, and a gas is going to completely fill the flask. All right? So there's a fourth kind of matter, which we don't talk about a whole lot, and I think the author of this textbook puts it in here simply because it's interesting, right? So plasma is a gaseous state of matter that contains an appreciable amount of electrically charged particles. In other words, it's a mess. That's what that means, all right? So plasma has unique properties distinct from ordinary gases, and they are found in stars, lightnings, and TV screens. Okay, so here's a picture of plasma. A plasma torch can be used to cut metal. So what you have coming out of here is just a really hot gas with lots of charged particles in there, and it's a mess. Okay, so plasmas, like we see in lightning bolts, you don't want to touch a plasma. And of course, you can't stick your hand inside a TV screen. These are old TV screens, not the TV screens you guys look at. But you guys remember a cathode ray TV? Cathode ray. You guys ever seen a TV that looks like that? Right? It looks kind of like this, and it's got a tube. Right? That's how TVs used to look. Right? Okay. So cathode CRT screen is what we're talking about when we say it's got a cathode ray has got a plasma in it. All right, so let's move on to the next terms. Mass is the measure of the amount of matter in an object. Weight is not. Weight refers to the gravity, to the force that gravity exerts on an object. We oftentimes think of mass and weight as the same thing, but they're not, right? So mass is m. Weight is mass times gravity. Right? That's the force. This is weight. Weight is the force. Is the force on a mass that gravity puts on it. Right? The acceleration due to gravity. All right, so we're mostly going to be using this term here. I just want to distinguish that and say, if you say weight, of course, we're not going to be in class a whole lot this semester, but if we were in a conversation and you said weight, I might stop and go, no, you don't mean that, you mean mass, okay? And so, anyway, there we go. An object's mass is the same on the Earth as it is on the moon, but its weight is different because gravity is different on the moon. Okay, so let's talk about the law of the conservation of matter. We're talking about this chapter is really mostly about matter, okay? So the law of the conservation of matter says that no matter what you do, you're not going to make or lose matter. Matter can be neither created nor destroyed. Now, of course, that was before E is equal to mc squared, right? Where we could take matter and we could do a nuclear reaction, we could blow something up, right? And so in that case, matter and energy are equivalent by the square of the speed of light. So the law of the conservation of matter is only true under normal circumstances. If you make a nuclear bomb, then yeah, you're gonna lose some matter, or make some matter, right? All right, so this is true. The law of the conservation in all the circumstances. This is not us. That's physics, right? So in our cases, the law matter can be neither created nor destroyed, neither in chemical processes nor in physical processes, besides nuclear bombs, right? Okay, so here are a couple examples of the law of the conservation of matter. If you take a bottle and you put some microbes in there and some sugar in there, and you seal it up right, and you put it at the right temperature, the microbes are going to make ethanol, and they're going to make carbon dioxide, and you're basically going to make beer, okay? Well, at the beginning, if you have, let's say you've got 5 or let's say 15 grams of stuff in there, in the end, you're going to have 15 grams. And that's what that's about. Now, some of the carbon dioxide could bubble out, and you might end up with 14 grams later, but you lost some mass in the form of a gas, right? And the same thing goes for batteries. We could say the same thing for batteries. Let's move on. So an element is a type of pure substance that cannot be broken down into simpler substances. You've seen elements before, the periodic table of the elements. These are the building blocks of nature, right? There are 100. There are over 100 known elements. 90 of these are natural, and then we've gotten a couple dozen of them that we've made in laboratories. Okay, so the periodic table of the elements, you've seen this before, and it is super useful to us. Has lots of information in it, and it's organized in a very nice way. Thank you, Dmitry Mendeleev, for suggesting this, because we now can make tons of predictions just based upon this. So cast your eyes on this. Look at it. Love it. Be the periodic table. All right, so atoms and molecules is the next couple terms I want to talk about. An atom, I'm going kind of fast here because we're not going to spend a lot of time on it in class, but an atom is the smallest particle of an element. I was talking about something just a couple days ago, a conceptual map to another professor, and I used the term atomized. I said, we believe that this domain can be atomized. And what I meant by that was, we believe that it can be broken down into the smallest particles, right? So the smallest particles of matter are elements. Now, molecules consist of 2 or more atoms connected by bonds. All right, you've seen that stuff before. So let's look at an example of this. Gold atoms, gold atoms, right? So here's a bunch of gold. There's a gold nugget, all right? That would be pretty valuable. There's a bunch of gold atoms put together, right? And a scanning tunneling microscope can generate views of surface solids. So each little dot you see there is really an atom, and that's awesome, isn't it? Each of those dots are really an atom, and that's the best picture we can get of atoms. We've got some slightly closer than that, but that's about the best we can get. So atoms are the smallest pieces of matter that we can possibly get. If we break it down, atoms are the smallest pieces of any element, but you can break an atom down into different things, but they no longer belong to a particular element. Okay, now molecules, as we said before, are when you have two or more atoms that are bonded together by bonds. So if you have hydrogen here, here's a hydrogen atom and here's a hydrogen atom. We haven't drawn the bond there, but we might draw it like a stick, okay? Oxygen, 2 atoms of oxygen stuck together by a bond. Phosphorus, actually, in its standard state, goes together as P4. Sulfur, oddly enough, goes together as S8. Okay, that's the standard state of sulfur. But these are all molecules, and they're held together by bonds. Okay, here are a couple more examples of molecules. These are no longer elemental molecules. These are compounds, right? So a compound might be water, where you have 2 hydrogen atoms and 1 oxygen atom, which you can't see my O because it's red, right? Carbon dioxide is another compound, which is made of atoms from different elements, and glucose. Here's another example of these. These, of course, just cartoons of these, right? They don't really look like that. Oxygen's not really red, right? And hydrogen's not really white, but we use these a lot of times. It's the third domain, right? A symbolic domain of chemistry to help us sort of appreciate how these things are bonded together. So now that we talked about atoms and molecules, let's talk about substances. So pure substances and mixtures pure substances have a constant composition. Elements are pure substances because they cannot be broken down into simpler substances by chemical changes. All right? And they're really pure because no matter what sample you take within that, no matter what piece you take of a particular sample, you're going to have the same thing. That's what we mean by pure substances, okay? Compounds are pure substances that can be broken down into simpler substances by chemical changes. They can be broken down into elements, right? And the properties of compounds are different from the elements that make those up. We'll definitely get into that a lot this semester, okay? So here's an example. Mercury oxide, mercury 2 oxide, can be broken down into mercury. The symbol for that is Hg, and oxide, which is O, right? Mercury oxide can be broken down into its elements, mercury and oxygen, okay? And we can do that by heating it, right? Now, a mixture is composed of 2 or more types of matter that can be present in varying amounts. That's really the key term here, in varying amounts. And they can be separated by physical changes. So evaporation is an example of a physical change. And there are 2 types of mixtures, homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures and heterogeneous mixtures, where homogeneous means it's the same everywhere within the mixture, and heterogeneous means it's different in different parts. I've got some examples and pictures of that. A homogeneous mixture exhibits uniform composition. That's really the key word here. And it's the same throughout. And another name for a homogeneous is solution. By far and away the most important mixtures we're going to be interested in this semester are homogeneous mixtures. Heterogeneous has compositions that vary from point to point, and they're less interesting to us. So here's a heterogeneous mixture, right? So if you take, this is oil and vinegar. If you take that oil and vinegar and you look at a particular part, you might see some bubbles in it of varying sizes and so on. So you can imagine, let me get a different color here. You can imagine if I took a sample here and a sample here, I have different things in that sample, right? I've got in this one, I got more bubbles. In this one, I have less bubbles, right? So this is homogeneous. Now in Gatorade, if you don't shake it, okay, in Gatorade, it's going to be a solution. It's going to be homogeneous. And by the way, those words are so alike that I sometimes will say them backwards. So if I said them backwards a minute ago, bear with me. Go real slow and look at that real carefully. Where am I here? Go real slow and look at, where am I here? Look at that real carefully and appreciate. This is hetero, saying that slowly, heterogeneous, and this is homogeneous because it's the same everywhere. Okay? Now let's look at, this is a nice little flow chart. I'm not going to walk you through this because it's really going to take practice. You just need to practice this. Matter, if it has constant properties in composition, yes, then it's a pure substance. No, it's a mixture. If it's uniform throughout, it's homogeneous. If it's not, it's heterogeneous, and so on. All right? So that's a lot of terms. We're going to need a lot of practice here with this. Chapter 1, Section 2. It is foundational. We're going to practice these a lot in class and in our homework assignments. All right. See you soon.